Okay, everyone. Now we're going to talk about the dreaded stoichiometry, which is a concept you may or may not have heard of before. And this is going to follow directly from the balancing chemical equations discussion. So we're going to talk about what you can, something important you can do with the information from a balanced chemical equation. So remember, a balanced chemical equation doesn't just tell us what reacts and what's formed, but it tells us the ratios in which they react. So if we have something like H2 plus O2 produces H2O, well, we know when we balance it, it tells us that we have two molecules of hydrogen reacting with one molecule of O2 to produce two molecules of water. So there's a ratio. Every one molecule of oxygen requires two molecules of O2, every one molecule of O2, oxygen requires two molecules of H2, of hydrogen. And they together will produce two. So if I had 10 molecules of oxygen, I would need 20 molecules of hydrogen. Or if I had 18 molecules of oxygen, I'd need 32 molecules of hydrogen, and so on and so forth. But as I mentioned before, any relationship or ratio that holds when we're talking about molecules and atoms, we can scale up to moles. Because remember, I just said, if you have 15 molecules of oxygen, then you need 30 molecules of hydrogen. Well, we can scale that all the way up to 6.02 times 10 to the 23rd molecules of oxygen. If I have 1 mole of oxygen, then I need 2 moles of hydrogen. And every fractional amount thereof. I just always need twice as much hydrogen as I have oxygen, and I will always produce the same amount of water as I put in as hydrogen. So this is our fourth little tool that we can use. So remember the other three I had, Avogadro's number converts between moles and number of particles. So actually I'm going to take stock here. So Avogadro's number, 6.02 times 10 to the 23rd. This helps us convert here. So I'm going to draw a little map this way. So moles is in the center. Moles is sort of our linchpin to everything, moles of A. If I want to convert to particles of A, I need Avogadro's number, 6.02 times 10 to the 23rd. If I want to convert to grams, then I need the molar mass of A, whatever that is, which we find from the periodic table. Now, I did this before. I did moles of A to moles of B, and depending on what moles of A, the relationship between moles of A and moles of B are, that's where our conversions are a little bit different. We kind of have two variants of this. One is where A or B, one of them is an element within a compound. So if I had, this sort of relationship here, this ratio would be something like 6 moles of carbon to 1 mole C6H12O6, right? I'm getting that from here. I'm getting it from the formula. Or if A and B have a different relationship, so this is for if, B is, carbon atoms and A is C6H12O6. But sometimes we have two different substances that have a different relationship. And in this case, this newest conversion is if their relationship is they are two different substances that are both related by being in the same chemical equation, the same reaction. So let me show you an example of that. Okay, so let me show you an example. So going back to this example, so let's say I had 3.89 moles of oxygen, and I wanted to know how many moles of water would be produced. Well, one thing I want to make totally clear. this relationship I'm about to show you, this ratio, this works with any two substances in the equation. You can go any which way you want. You can go from reactant to product, product to reactant, reactant to reactant, product to product. It doesn't matter. The only thing that will change is the language we use to describe it. So because I'm going from reactant to product, I'm saying how much water will be produced when this much O2 reacts. And of course, the assumption being we have enough. Well, I wrote this equation all stupid. I'm sorry. There we go. That's better. Now it's balanced. And of course, we're assuming we have enough hydrogen to react with this amount of oxygen. It's sort of an understood. Right now, we're really just relating the oxygen and the water. So I'm going to put on the bottom moles of O2. So it's really important that we label moles of what. We can't just put moles, because I'm going to put in the numerator moles of H2O, right? So it's moles and moles, but it's moles of what? Now, these two are related by the chemical equation. So what I'm going to do is I'm going to put in the numerator the moles of water, and where I get this number from is literally just the coefficient in front of water in the equation. So I put a 2, and then in front of oxygen there's nothing, so I put a 1. So we just take 3.89 times 2, and I get 7.78 moles of water. So that's how many moles of water I make. Right? I could do another thing. I could say, well, I would get kind of the same answer. I'm going to move on and try some different examples. So the study of these relationships is called stoichiometry. So this idea is called stoichiometry. One thing I want to point out, I'm going to start adding in the next slide, I'm going to start adding more steps. But whenever you have a stoichiometry problem, and you can identify a stoichiometry problem fairly easily because they all kind of do the same thing generally, which is they give you have an equation, or you have the ability to write a balanced equation, and you're given one of the substances somewhere, some information about one of the substances somewhere in the equation. Product, reactant, doesn't really matter. And you're asked to find out information about one of the other substances in the reaction. And at the core of every stoichiometry problem is this step, this mole-to-mole conversion using the coefficients. So remember, given the molar mass of the compound, we can convert between grams and moles. So we can have, the problem can be asked with a few more steps involved. For example, 1 mole of CH3 will produce 3 moles of CO2. And here's the kind of question we might get. How many grams of N2 do we need to produce 7.5 grams of NH3? So notice the wording is a little different, right? So I'm saying, I want this much ammonia, right? How much N2 do I need? I'm not asking about the H2. We could do that next. But I just want to know how much N2 I need. So it's going to be basically the same. But how many grams of N2? So remember, at the core of this problem is going to be this step. Because I'm converting from NH4, or NH3, I'm going to have moles NH3 and moles N2, because that's what I want to know about. And in the numerator, of course, is going to be a 2 because of this 2 here. And down here will be a 1 because there's an understood 1 here. Now, the problem is I have 7.50 grams of ammonia. And I can't cancel this because I need to know what? I need to know moles. So first things first, I've got to convert from grams of ammonia to moles of ammonia, right? So the molar mass is going to be the mass of nitrogen plus 3 times the mass of hydrogen, so it's 17.04 grams per 1 mole. And now that I've got moles of ammonia, I can use this step up here. I can do moles of NH3, moles of N2. And again, I just want to emphasize, these where these come from is right here, is these coefficients. Nothing else. You don't worry about this number over here. It's just the coefficients. So then this cancels. And I want to know mass of N2, so moles N2, grams N2, and I need to find the molar mass of N2, which is just going to be the mass of nitrogen times 2, so 28.02 grams per mole. So now all I do is just take 7.5 divided by 17.04 times 2 times 28.02. And so now I've got 24.7 grams N2, because we have to keep the 3 significant figures because of this number we started with. So there we go. Okay, so moving on. So that is basically, what I've shown you is basically how stoichiometry works. So I want you to pause it and try this problem here, and then we'll move on. Okay, so there's 2 parts to this problem. So a piece of chromium with mass 0.175 grams of chromium, right? What mass of chromium 3 oxide is produced if the metal is completely converted to chromium 3 oxide? So first things first, we got to get into moles. Hopefully you're realizing by now that just about any problem you ever have, the first thing you need to do is get into moles, because we can't do really anything with grams. So we need to convert to moles. So here's the molar mass of chromium. Now I'm going to do this important, sort of the heart of the stoichiometry step. So moles of chromium here, moles of what I want to know about, Cr2O3 up here. So then I'm going to put, because there's a 4 in front of chromium, I'm going to put a 4 here. And because there's a 2 in front of chromium 3 oxide, I'm going to put a 2 there. And then, do that, moles of Cr2O3. And we want to know mass of Cr2O3, I believe. Yeah. So now I just need to look up find the molar mass of Cr2O3. So I had it paused, and I have no idea how long it's been paused. So I will say this and pick up where I was. The mass of chromium that we're starting with is 0.175 grams of chromium, and the chromium 3 oxide is 0.256 grams of chromium 3 oxide. So that's the answer we get. I don't know where it cut out. I have to go back and check the video. And so that's the answer for this first part. The second part is we want to know the mass of O2. Now, what's important to know is that we can actually get there from chromium or chromium 3 oxide, because these are already sort of figured out in alignment with one another. They are already sort of synced up, right? And I'll show you that we can do both, and we can get there. So I'm going to convert from grams of chromium to moles of chromium. And then I'm going to convert from moles of chromium to moles of O2. Now again, notice the wording is just a little different, but what I'm doing is exactly the same, right? So in the first part it was what mass of this is produced if the metal is completely converted. And then in this part it's, what mass of O2 is required for it to react with it. So, you can do the problem the same, it's just the way it's phrased will be a little different. So 4 moles of chromium to 3 moles of O2. Right? Now notice, I want you to be aware that the number here doesn't affect the number in front of moles here, right? We're just converting from grams to moles. We just want to know the mass of 1 mole of chromium. This number is specifically about relating it to the other things in the equation. It's not changing the identity of the chromium in any way. So it's only important for this step here. And then we'll convert from 1 mole O2 to 32 grams of O2, and then we should get an answer. Now I'm going to do the same thing down here with chromium 3 oxide. It's 152 grams of chromium 3 oxide to 1 mole of chromium 3 oxide. So in the bottom, I'm going to put moles of chromium 3 oxide, moles of O2. And so I'm going to put, again, 3 in front of oxygen, moles of oxygen, because that's what's up here in front of oxygen. And then down here I'm going to put 2, because that's what's here. And then I'm going to multiply times 1 mole of O2 to 32 grams O2. So the first one, I get 0.0808 grams of O2. And we should, if I did everything right, get the same answer or something really close for the bottom, and I get 8.0808 grams O2. Now, there was a little bit of a rounding difference, a few significant figures, like another significant figure out. There was actually a rounding difference. That's okay, because, this is the last significant figure, so that's where you're going to get those issues, because we rounded off here, really. So, anyway, so that's how we do that. Let's do one more problem. Try this. Try these two. The equation should be balanced already. And there we go. So try these, and I'll come back. Okay, so in the first problem, we're starting with 6.44 moles SO3. Now, what I want to do, I don't need to convert to moles because I'm already in moles. All I need to do is now go directly, so I've got moles SO3, moles, I want to know about PBS. The relationship is just 1 to 1, and I get that from the balanced chemical equation here. And then all I need to do is convert to grams, so moles PBS, grams PBS. And so I just have to take the mass of lead plus the mass of sulfur, 239.27. And so my answer is 6.44 times 239.2. That looks kind of like a 7. It's hard to say. 239.2. And when I multiply everything together, I get quite a lot. I get 1,540 grams. We should only have 3 significant figures. Or you could do 1.54 times 10 to the 3rd grams, or 1.54 kilograms. Okay. Now the second part is how many molecules of O2 is required for the reaction. Okay, well, 6.44 moles of SO3. In the bottom, I can put 1 mole SO3. And the top is 2 moles O2. Again, getting these numbers from the chemical reaction. And then, I'm not being asked to go to grams. So take note, I can change it up on you. I don't want to go to grams of O2. I want molecules. I want O2 molecules, which is going to require Avogadro's number. 6.022 times 10 to the 23rd. And so, my answer is going to be 7.76 times 10 to the 24th O2 molecules. And there we go. Oops, cut it off. 7.76. There it is.